Okay, so I'm recording just for those people that are going to have to catch this up. What I want you to do today, you're going to do a bit of an investigation into the graphs of the functions that we've looked at in terms of direct and inverse proportion, so that you can understand where graphs are showing direct proportion, whether it be linear or whether it be different, non-linear direct proportion. Okay, and then the graphs that do show inverse proportion. Okay, so we have a formula: y equals kx is for direct proportion. Yeah, we all happy with that? But what we've also done is we've looked at different powers, haven't we? So we've said kx squared or kx cubed or so on. So what I'm going to do is I'm going to put kx to the power of n. Now, when you put these letters, other than y and x, into Desmos, it offers you sliders. So I'm just going to click all, and I'm going to get these sliders. Now, what you have on the screen at the moment is where k is 1, so we've got 1x to the power of 1. So that's just y equals x. And it's showing direct proportion. That's the behavior of it. Now, the thing about the sliders, it enables you to change the values quite quickly without having to retype them in. So, for instance, I can change the 1 to, I can slide it, or I can type it in and press a 2. So what do you notice? Kx to the power of 2 is now a quadratic, isn't it? It's a parabolic quadratic function, right? We've done that, but put to the power of 3, and so on, yeah? Right, what I can do here, look, I can say, if I like, I can set up an animation, and I can say, well, I'm going to start n as 1, and I'm going to go up to 10, steps of 1 up to 10. What that means is that if I press now animate, it's going to start at 1 and flick through it for me, so I can see what's happening. All right? And I can look at it and go, right, what is happening? Are they all showing me direct proportion? What's the behavior? What can I see? All right? Now, what we can also do is we can set up our animation speed. We can loop it backwards and forward, but that's up to you. That's incidental. Okay? What you might want to do is, though, instead of going up in ones, what happens if I go up in 0.1s? You could try that. So what if it was kx to the power of 6.1, for instance? So if I now put that in, 6.1, what do you notice? Half the graph disappears. So Neil, if you want, or anyone else if you want to, but I'm expecting Neil, an explanation of why. That'd be the extension for you. Why has half my graph disappeared for 6.1? Because if I press 6.2, look, it's there. If I do 6.6, it's there. Okay. Right. The other thing I can also do, look, I can change. So if I go back to n to the power of 2, I can change the k value and see what happens to my graph. Okay. All right. So I'm looking at what kind of graphs can I produce. Now, don't forget, there are also negative values that I could put in, and you can see what would happen. But what we can also do is we can look at the y equals k divided by x to the power of n, and see what happens. Now, once I've finished with 1, I can just switch it off. I don't need to delete it. All right. I can do the same. These sliders also control k and n in this one as well. So you notice what's happened. I've got at n is 1, We're used to seeing that one, right? Shape. What type of function is that one, Daphne?
That one.
That's a reciprocal function, yeah? All right. Again, what happens if I make n positive, negative, decimal? This is what I'm after you. So I don't want answers yet. Give people, if you've already had 5 minutes or so to have a bit of fun. Write these things down in your book. All right. So you can put a title of exploring the graphs of direct and inverse variation. And maybe I would like to know, well, what happens if k is positive or negative or certain values? What if n is positive or negative? Do we still have direct and inverse proportion? Because what we're looking for with this is, can we understand more so that we're not tricked into saying something is direct variation when it's actually not anymore? All right? That's what I'm after, you to get some understanding. So if an exam question says, does this show, and you just look at the function and go, yeah, that does. All right, maybe you'll understand. Is that clear what you're doing? Just going through it. Like I said, why does half the graph disappear? With this one, when I'm 4.7, for instance, half my graph has disappeared. Why is that happening? If you can explain, that would be great. Right. And I don't think it's as easy, Neil, as just saying when it's odd. Because look, what if it's 3? Oh, look, we have an entire graph. Yet if it's 3.2, we have an entire graph, but if it's 3.1, we have half a graph. So what would be the mathematics behind explaining why? Now, if you like, I can also give you a clue, which is if you click on the function now, Sam, no? If you click on settings, you can actually convert it to a table of values. That might help you understand. All right. Right, so let's just quick review. So this way, Sam, you can tell us, what do we know about, so we've got k x to the power of n. What do we know about our graphs that show us direct proportion? So will it always show us direct proportion, or have we found times when it doesn't? Yeah. Okay, when n is negative. So if I go into the negatives, it's no longer showing me direct proportion. In fact, what is it showing me? Can you explain why? So we know that as a reciprocal function, right? Can we explain why a negative power of n? So let me just write this. So it's on the video for later. Why would a negative power of n stop showing direct? So we've got k x to the power of n, but when n is positive, we're okay, but when n is negative, we're not. So that's not direct proportion. And that's because, let's think of an example. So we have y is, say k is 1, and just say x to the power of negative 2. Why is that no longer showing direct proportion? Well, again, laws of exponents. What's another way of writing x to the power of negative 2?
1 over x squared.
Okay. So that, you will recognize that as inverse proportion. Okay. So on our graph, we can obviously see we're not going to have negative, so we've got a negative n. So we're kind of limited with n's being positive. Now, what about the same thing with the inverse? What happens?
If n is positive, then n is negative.
Yeah. Exactly. So what we're looking at, guys, is when we're looking at variation, n has to be positive, right? N has to be positive, otherwise you mess things up. All right? So if we are not going to be saying to you y is varies directly as x to the power of -3. It's always going to be y varies directly as x to the power of 3 or 4 or 5 or 6 or so on. Okay? So when we talk direct, we're going to limit. So I'm going to change my n to not be negatives at all and just be positives. All right? Now, what happens to the function when k increases? Okay, when I've got n to the power of 1, k, what does it do? Okay, changes the slope. And what does a slope mean in terms of a proportional relationship? Yeah, so how much one of them will change relative to the other one, yeah? Right, so it's the difference between my two values, isn't it? So I've got, what one value is always common? 0, 0, right? You notice all my graphs go through 0, 0. So the difference between when k is 2, all right, that means you find one number by multiplying by 2. If k is 4, you find one number, so the graph will be steeper. So how do we find k from a graph? It's the slope, rise over run. Until we go up to a different one. So let's say when when n goes up to 2, to 3, to 4, right, what is happening then? So if I increase k, it still increases the slope, right? So the relationship sort of maintains the same, although the relationship as the power goes up changes something, doesn't it? Now, can I ask you, this kind of cubic one, what would be the relevance of these negative values? Would we ever have need for a relative negative in a variation question? So two things vary directly. This is what it would look like if it was very cubic. Do we have normally, when we're talking variation, negative values of x and y? Would it make sense? You've been doing light intensity and distance. Would it make sense to have negative distance and negative light intensity? Potentially, actually, because there was a question that you may have done, or maybe not because they didn't have it at the time. In the M2 textbook, there is a measure of light intensity from stars, and it's all relative from a particular point. So some stars have a negative light intensity and some have a positive, depending on, you know, whether they're brighter or dimmer than the marker. So it could be relative to our sun. Some stars will be dull compared to our sun, some will be brighter. So light intensity could be a negative value if our sun is considered 0. So we could have that relationship, all right, but in specifics. All right, I also then asked you to look at the inverse, recognize the inverse ones, yeah? As reciprocal functions, we've already gone n must be positive. As k increases, we've talked about this, yeah? The slope of the graph changes. All right. Are there any powers that can't be? So if I did 0.1, half of it disappears. So the negative side, now we've talked about that, haven't we? Because of the negative roots and things like that. We can't do the root of a negative, all right? But will it matter in terms of our variation problems on the whole? No, because generally, what are we concerned with? Only the positive quadrant normally, okay? But hopefully you've also recognised, look, that before we go, would you recognise that as a reciprocal function now? Because you've always said if I asked you to draw a reciprocal function, you've kind of done the opposites, but now you hopefully will recognise that as a reciprocal function as well, which will show what kind of variation? Inverse variation. Okay. All right, we'll move on.